Good afternoon, everyone. Welcome to another in the series of our CXC Students Workshop. And today our focus will be circle theorems. Welcome from myself, Judith Hemmings, and my co-host, Janice Hales, Mrs. Janice Hales. Thank you for joining us this afternoon. Let us begin. Good afternoon, everyone. Welcome to another in the series of our CXC Students Workshop. Before we begin, before I begin our activities for the afternoon, we are going to be looking at a little activity. We'll be going into a little fun activity, and we welcome you to participate. It's called 3 Picks, 1 Word. And we'll be giving you 3 images, and we want you to think of 1 word that could be used to describe that particular 1 word that will describe all 3 pictures that you're looking at. So this is the first one. Let's go.
Go ahead, students. Feel free to share your answers in the chat.
Thank you, Janice. All right, so this is our first activity. So look at those 3 pictures. What is the 1 word that comes to mind? Provide a response in the chat, and then we'll expose the answer that we have. All right. Okay. Count the numbers of blocks needed to form the words. I'm seeing.
All
Okay.
right. Shane Lynn has said angles.
All right. Let's say Shaylin is correct.
Acacia angles as well.
Okay. So we do have a couple of winners, Janice. Let's
Yes.
give them another one, Mrs. Eels. Let's give them another one. So you're going to look at the 3 images. What immediately comes to mind, bear in mind that the topic that we'll be doing today. All right.
Shaniqua Davidson says cord. Waterman says cord. Benicia Wilson says cord.
Okay, let's see if they are indeed correct. Okay, I'm giving virtual claps now to all the winners.
Congratulations. Yes.
Very good.
We
All
have some
right.
students here who are very quick
Right.
at
There was another.
identifying similarities. All right, there we have another one. Let's see who is going to come up first. I'm watching and I'm waiting. Davidson says point.
Okay.
Shane Lynn says points. Brittany
Right.
Britton says center.
Center. Okay.
And I'm seeing Rickesia Waterman saying center as well.
Right. Let's see if we are in agreement with any of those responses given so far. All right. Okay, center, spell the British way. All right. Let's see if there are any more for us here. Okay.
We have one more.
All right, this one may be a bit more challenging, but let's see if you're on point. Okay, I'm seeing a response already from a Shanika and Ashanti.
Right, Shanika says tangent, and Ashanti says segment.
Right. Okay, let's see which of those persons are correct, if any.
And the winner is Shaniqua Davidson.
Yes, very good students. Very
Good
good.
job.
Good job. All right, so today we are going to explain to you a bit what is it that we're going to be doing. So the focus of our session today, as I said before, is all about circle theorems. And we are going to be looking at the properties of circles and circle theorem to use those to determine angles. We're also going to be solving problem using the theorems related to properties of a circle. At this time, though, before we go into the meat of the matter, which is all about circle theorems today, there might be a few things that you might have forgotten about angles. So my co-host, Mrs. Hales, will be taking you through some activities that will help refresh your memories about some basic concepts about angles. Mrs. Hales, over to you.
All right, thank you, Ms. Hemmings. And as we go into that process, we're going to start with concepts that you would have perhaps been exposed to during your second form years. And those angles are angle properties. And the first one we're going to look at are vertically opposite angles. You remember anything about vertically opposite angles? If you'd like to speak, you are free to indicate using a raising of your hand so that we can hear what you have to say. I'm seeing Shaniqua here saying that they are equal. All right, so that vertically opposite angles are equal. And how do we identify their location? When we say vertically opposite, how do we identify their location? All right. Now, vertically opposite angles are pairs of angles formed where two lines intersect. And when these angles are formed, we identify them because they are positioned somewhat vertically, one above the other. If we look at the angles here in terms of their formation, where one line is cut by another, we see that angle A measures 56 degrees and angle B is adjacent to angle A on that straight line. And if we were to calculate the length of the size of angle B, we recognize that angles on a straight line measure, let's see, angles on a straight line measure
I'm seeing,
180 degrees.
right.
Great. Shaniqua is on the ball. And
Yes, she
so,
is.
therefore, we could calculate the size of angle B. All right, and what would be the size of angle B? Let's see who is going to give me the size of angle B right now. Size of angle B. It is adjacent to angle A on the straight line, and the sum of the angles on the straight line is 180 degrees, and Davia says 124 degrees, and that is true.
And
And so
Ricky
if
as
we,
well.
and Rikia, okay, great. And so if we were to calculate the size of angle C, also being on a straight line and adjacent to angle B, what would be the size of angle C? Somebody is saying they're not hearing. Let me just check on that, team. All right, what would be the size of angle C? 56 degrees. Excellent. So we see that angle C is adjacent to angle A on that straight line. And if we were to calculate the size of angle C, what would be the size of angle C?
So 56 degrees from Benika and Rikia, those answers are correct. All right. Okay, so could we move to the other slide if possible? All right, so vertically opposite angles, as my colleague was explaining before, they are angles that are of the same size. And as was shared in our chat, angles A and angle C would both be equal. It therefore means that angle D and angle B would also be equal. All right, so keep that in mind. Vertically opposite angles are formed when two lines intersect each other. And you find that the angles that are opposite to each other in those intersections, they are both equal. And also, sum of angles on a straight line would give us 180 degrees.
All right, thank you, Ms. Hemmings.
Sure.
And so we recognize that these angles, the sum of the angles on a straight line measures 180. So we summarize these concepts. All right. And in addition to that, we also recognize that angles at a point sum to 360 degrees. I should have given you a chance to figure that out. All right. But if we were to add all the angles A, B, C, and D, we would recognize that the sum that we'll get at that point totals 360 degrees, 360 degrees. So the vertically opposite angles are angles A and C, and those two angles are vertically opposite. And the other pair of vertically opposite angles are B and D. Good. Let's look at another concept relating to angles formed when a pair of parallel lines are cut by a transversal. And here we see a number of angles here, but our focus will be corresponding angles. So let me see, what do you remember about corresponding angles? If you'd like to speak, feel free to open your microphone and answer. If not, go ahead and type for us in the chat what you remember about corresponding angles and how do we identify angles which are corresponding to each other. All right.
All right, I'm seeing an answer in the chat from Shanika, and she's saying, I think they add up to 180 degrees.
All right, thank you for that response. Think about it a little bit more, just to see if you'll be able to do some calculations with that based on the diagram that we have and to see if your answer is correct. We'll respond to that in a minute. Somebody said Z angles. I'm seeing here Z angles. All right, so corresponding angles are not the angles we normally refer to as Z angles. Vanessa here is saying they are equal. All right, so that is the answer we're looking for. Indeed, they are equal, but how do we identify them in this diagram, the angles that are corresponding? Can you share with me, based on this diagram, which angle is a corresponding angle to angle A? Angle A, which angle is a corresponding angle to angle A?
Shanika is saying AE, angle E.
All right, great, Shaniko. It would be nice. We're getting
And
some
so is
responses as
Vanessa.
well. Great.
Right.
It would be nice first for you to tell us, how do you know that those two angles are corresponding as we work within the time frame allotted? How do we know that angle E is corresponding to angle A? All right, very short and sweet. They are located in the same position. All right, so based on where they are located on each of the lines which are parallel that are cut by the transversal, we see that A is above that line on the left and C is above the second line on the left as well. And so corresponding angles are equal. All
just
right,
just to add that on our YouTube channel, that a response was also provided saying angle E, and Chanel is saying that E is the corresponding angle. So we're also getting some responses from YouTube.
All right, great. That's excellent. All right, can we find another pair of angles which are corresponding based on this diagram? Go ahead quickly, type for us in the chat another pair of angles which are corresponding angles outside of A and E. We're not talking about A and E anymore. Do we see any other pair of angles which are corresponding angles? Yes, miss. All right, tell me, share with me which angles those are. So we are having B and F, C and G. All right, and
D and
E
H.
and H. Excellent. So you remember those concepts. All right, so two parallel lines intersected by a transversal form corresponding pairs of angles, and they are equal. All right, so by way of notes, you can jot that down. And that yellow line that is intersecting the parallel lines, we refer to that yellow line as the transversal. So the transversal is intersecting two parallel lines. And so corresponding angles which are formed, angle A is equal to angle E, angle B is equal to angle F, angle D is equal to angle H, and angle C is equal to angle G. And co-interior angles is where we are now. So let's go to co-interior angles. What are co-interior angles? Co-interior angles. All right, so we have already that information displayed. So co-interior angles lie between the two lines on the same side of the transversal, and co-interior angles sum to 180 degrees. Very good. Now, can you identify for me two angles which we regard as co-interior angles? Give me a pair of angles which are co-interior angles based on our recollection of the definition as well as what we have displayed here. Two angles which are co-interior angles.
Benika is saying that D and E, Giovanni is saying D and H, and K Akia, I'm getting the names correctly, is saying B and C, and Ashante is saying A and F.
A and F. All right, so we need to clarify some of these. So the correct response for, I think, of the ones that I have seen, if my memory serves me right, would be D and E. All right, D and E, and I'm also seeing C and F, right? Those are co-interior angles. They are on the interior part of, they're on the same side where the transversal cuts the parallel line. So D and E, C and F are co-interior angles.
Our students on YouTube, Ricardo also said D and E.
D and E, very good. All right, so we are now looking at alternate interior angles. Alternate interior angles. What do you remember about alternate interior angles? I think you normally refer to them as alternate angles. They
Um,
are equal.
uh,
Okay. All right. So I'm going to take that response. How do you identify alternate interior angles? How do you identify them? What do they look like?
Benicia added that they are Z-shaped angles and are equal.
Yes, they have that Z formation. And so we're talking about the angles on the inner part of the arms formed by that Z. So can you give me pairs of angles which are alternate interior angles? Give me some pairs of angles that you say are alternate angles. C and E, good. Any other? Any other? C and E. Are we getting any other on YouTube?
I'm checking.
All right, so we're seeing D and F as well. All right, good job. So our alternate angles here are D and F and C and E. All right, good job. Now,
On Facebook, sorry, not on YouTube, Sabrina said C and E,
C and E. Okay,
and she's incorrect. She's correct.
she's correct. All right, great.
Correct.
All right, so we're focused now on properties of circles. Now, when angles, triangles, and quadrilateral are constructed in a circle, the angles have certain properties. And today we're going to be examining those properties, and those properties are what we refer to as circle theorems. And our aim this afternoon is to focus on 8 such theorems. And here are the first 4. We're looking at subtended angles, angles at the center and the circumference, angles in a semicircle, angles in a cyclic quadrilateral, angles between a tangent and a radius, tangents from a common point outside the circumference, alternate segment theorem, and angles between a radius and a chord. So we have quite a bit that we want to get through today. So we're going to need you to participate fully with us. So if you would like to get your protractor and your compass and come and sit down and talk with us so that you can carry out the activities as we go through, so that you'll have a better opportunity of understanding what it is we are going to be exploring. All right. So the first one we're going to look at is the subtended angles activity. We're going to look at the subtended angles activity. So giving you a minute, run, get your protractor, your compass, your plain paper, because you're going to be giving, we will give you some steps that will allow you to construct and to draw lines so that you can identify some of these angle properties on your own. All right. Also remember that we will have this video on YouTube for further reference if you'd also like to go back through the activity and do it on your own if you do not have the relevant resources at this moment. All right. So let's jump right into it. So we're looking at subtended angles, and here are the steps that you're going to go through to be able to identify this property. We're going to construct a circle and label its center O. All right, and then we're going to draw a chord to form 2 segments. And if you look at this chord in blue here, what it has done is to divide the circle into two segments, all right? And then in one segment, we're going to draw two triangles that share the chord as one of their sides. So we constructed the chord first, and then we went ahead and constructed two triangles as a result. Then we are labeling the angles that were formed by those two triangles at the circumference of the circle. We're labeling one A and we're labeling the other B. And we went ahead and did the measure of those angles. So we found that angle A measures 45 degrees and angle B also measures 45 degrees, has a measure of 45 degrees. Can you share with me the technical team? Just assist. I think we're having a little challenge here in terms of the speed of the presentation. So I would ask for just a little adjustments here. All right, as we pause momentarily just to go back. All right, here we are. So when we look at these two angles, the question is, what did you observe?
Giovanni is suggesting the angles are the same. The angles on the same chord are equal.
All right. So you say angles on the same chord are equal, but there's an important component missing from your definition. They're not just on the same chord. They're also in the same segment. Very good.
Good.
What else? They're on the same chord. They're in the same segment. And where are those angles located is another critical component for us to concretize. They're on the same arc as well. Very good. They're standing on the same arc or chord. They're in the same segment. And what else? Where are they located? Where they are located. They're
And the
touching the
circumference, Vanessa.
circumference. Very good. So, right, they're touching 2 points on the circumference. So, what we recognize is that the angles are formed at the circumference of the circle. They're standing on the same arc or chord, and they are equal. Now, one of the things I want to bring up here is that when you'll be sitting your examinations, you'll be required to answer questions relating to circle theorems. And for every value that you calculate in terms of the measure of an angle, you are required to give your reason behind that answer. So how did you arrive at that answer? So we knew that angle A is equal to angle B, and our reason is the observations that we're making from these presentations. So a nicely laid out observation we will have following now is that angles at the circumference of a circle subtended by the same arc or chord in the same segment are equal. So when you are pulling for a reason, you don't have to wrap your mind around how am I going to structure this. We have a nice little laid out reason here for you to use if that is the case. Now, there are critical components, so even if you don't remember this word for word, but there are some critical components that you must include. They are at the circumference of the circle, they're standing on the same arc or chord, and they are in the same segment, and therefore they are equal. So please bear that in mind. Now, in given any of the diagrams, they will not always look like the ones that we gave you in the first example, because we have different orientations of these diagrams that you'll see in various settings, but you still must be able to identify the properties regardless of the orientation of the diagram. So let us look at figure 1 here. Our green line indicates our chord, and we have angles at the circumference, angles P and Q. All right, and we see some other little lines in there, but our focus is on the principle or the observation about angles at the circumference of the circle standing on the same arc or chord. All right, so in this case, angles P and Q will be equal based on the first diagram. Let's turn our attention to the second diagram. It looks a little bit more complicated, but it is the same principles that we're looking at. And if we look at our chord, that's a green line there for our chord in our second diagram, we see that angles A, B, and C are in the same segment. Do you agree? Share with me. Do you agree that angles A, B, and C are in the same segment? We're going back. Do we agree that angles A, B, and C are in the
Shanique is
same?
saying yes, miss, and so
All
is
right,
Shane.
great. They're in the same segment. And do we agree that they're all touching the circumference of the circle? Are they all touching the circumference of the circle?
A lot of yeses coming in.
Great. And what other property should they have for us to be able to say that they're equal? We know that they're in the same segment. We know that they're touching the circumference of the circle. What else must happen for us to conclude, be able to say without a doubt that they are equal? We're looking at three things. They're at the circumference of the circle. They are in the same segment. What else?
Something
Something
with
with
the
the chord.
card. Yes.
They're
That's
standing on,
the
right, they're
same card.
standing or subtended. They're standing or they're subtended by the same arc or chord. Very
Right.
good. And if we look now at angles D and E, what can we say about angles D and E? Should either of them still be equal to the same values as A, B, and C? Why is it we have a different letter here? Share with me. Should
Shanika is
angles
saying no.
No? All right. So we want a little reasoning behind that now. Tell us, why did you say no? Because it's important for us to get your what you're thinking by explaining yourself. Why did you say no? Why is it that angles D and E would not have the same values as the same value as angles A, B, and C? Why not?
Shane, I'm trying to understand Shane's answer. He's saying point from the starting of the chord, P is P and the N is Q. And then Shanika is saying because they're in another segment.
All right, there in that is the response that we're
We're
looking for as
expecting,
well,
right?
right? So yes, they are in another segment, and so the two angles that are in that other segment would be angles D and E, and those two angles would be equal. So if you get a diagram, if you're given a diagram such as figure 2, you recognize that there are two segments, and therefore there are two different sets of angles that would have that you would need to calculate. All right, great. So moving on. So we're looking at this activity, and here it is. We have the chord. We can identify that chord, and we can see the angle, which is 47 degrees, which is formed at the circumference of the circle. And we're going to add a little bit more to this diagram. So here we have, very good. So we have additional triangles which are formed, and they're standing on the same arc or chord. So we can say it's standing on the same chord, or we could say it's standing on the same arc. And we have three of them, and all three are touching the circumference of the circle. And so based on the property, we can say that these angles are equal in measure. All right, now, is this property still true if the apex A is rotated into the other segment of the circle? Would that still hold?
Oops, we gave it away a bit,
Oh my. But I think they would have figured it out just now when we
right?
looked at the
Shane is saying no, ma'am.
all right, good. Angle subtended by a chord does not change as long as they remain in the same segment. However, angles subtended by the same chord in different segments are not equal, and we had looked at that property just now. Good. So we're on a roll. We are on a roll, and we say that angles subtended by a chord in the same segment are equal. All right, no, here it is. So when you go to CXC, remember, you're not going to be getting isolated angles, meaning as you look at it, you can see the property. No, you're going to be getting perhaps one diagram that has a number of properties right there, and you have to be able to zoom in on the ones that you're looking at or the ones you're looking for. All right, so here it is. Here's a big diagram that has a number of circle properties right in here, but we're looking for the property that is showing us that angles at the circumference of the circle standing on the same arc or chord are equal. Can you identify angles that would be equal now based on that property? Look at this diagram. and give me angles that would be equal based on this property. Somebody said D and G.
G.
All right, give us, and then you're putting a disclaimer to say I think.
And
All
then
right,
there is
so let's
Carif with B and C.
B and C. All right, so let me rephrase the question now. Identify a chord for me. Give me the two endpoints of the chord that you're talking about, and then tell me which two angles at the circumference are standing on that chord. So
Hale said
identify a chord
AB.
for me. All right, B and A. So identify the chord for me. Say the chord AD, for example. Let's talk about the chord AD. Good. Do we have any angles at the circumference of the circle standing on the chord AD that we could say are equal?
Shane, I think Shane is responding to the chord. He's saying the chord is AD, and Carif is saying B and C, which I think are the angles that he's identifying, I think.
Identifying. Are you sure? Because you must be able to move your hand up from the chord to go and touch that angle at the top. And are we
All right.
able to do that?
Vanessa is saying the angles are ACD and AGB.
AC,
ABG.
go again.
ACD and
ACD
ABG.
and ABG. Which chord are they standing on? Denicia? Are they standing on a chord? Because you have to identify that they're actually on a chord or an arc. All right. So let me give you a chord. Let me give you an arc that we're going to work with. What about the arc AG? Let's start with that one. AG. Look at the arc AG. Can we identify angles at the circumference that are standing on the chord, on the arc AG? So we're going up. The angle, if we're using 3 letters to identify the angle, it must start with A and end with G. So for example, one of the angles standing on that arc is ABG. ABG, standing on that arc, ABG. Give me another angle that is also standing on that arc. That
We have
starts
some
with
answers
A.
coming in.
All right, so go ahead.
Javon is saying ABG and ACG.
All right, ABG and ACG. All right, good job. Let's go back a little. Great. So ABG, that's the angle in red. The lines are marked in red there. And in green, we have ACG. Do you see those two angles coming from the same arc? Yes or no? Do you see that those two angles are touching the circumference of the circle and they're both standing on the arc AG?
And just to acknowledge that King from our YouTube and Tomoya are also saying ACG.
All right, great. Good job. So you see, this is what you're going to be up against when you go in your exams, you know. You're going to see a diagram that looks as complex as this one, but you have to be able to identify it clearly. All right, so going back for Ashanti, just briefly, come with us, Ashanti. Identify the chord AG. You can put your finger on the screen and open between your thumb and your pointer finger and come from AG and use your finger, touch your screen and go all the way up to angle B. Try that, Ashanti, and come back down to AG. Then go back up from AG, use your finger and go up to C. And tell me if you can see that those two angles are on the same arc. Did that help, Ashanti?
All right, there's a question. Okay, David Ashanti.
All right, good, good. I'm happy that you saw that. All the others, if you look at the other chords that are there, for example, CD, there's only one angle going to the circumference from the chord CD. Only one. If you go from CD and follow your hand all the way up, you'll see angle A touching the circumference, but there's no other angle. And we're looking at the ones where the lines are drawn in the diagram. We're not creating any chord. We're working with the lines that we already have in the diagram, all right? And if we look at, tell me now, from the chord BC, which angle comes from the chord BC and is touching the circumference of the circle? Which angle comes from the chord BC and is touching the circumference of the circle? Which angle is coming from BC and touches the circumference of the circle? And we have others here. G, very good. Is there any other angle that comes from BC and is touching the circumference of the circle? I think I just found another one. Coming from BC, no, you have to put your finger on the chord BC and go right up to the circumference and see which angle you see at that point. BC. So we saw G is one of them. A, very good, because we can go from the chord BC and go up to A as well. So angles A and G would be equal. All right. All right, great. All right, so that's it. So angles, so the main ones that we've pointed out so far is angles ACG and angles ACG and ABG. All right.
And
So
Mrs. Ailes, I think it's important that we point out that when we have found the correct pairs or the correct subtended angle, they end and start with they start and end with the same letters. So
right,
that's a
right,
hint that you have the correct
right,
pairs.
right, because they're coming from the same chord. So ABG, notice it starts with A, end with G. ACG starts with A, ends with G. CGB and CAB. All right. So good job. So we're going to come to this. Every property we look at, we're going to come back to that diagram, and you're going to have to be able to identify those properties, the properties of that in that diagram. All right. So now we're going to look at angles at the center and the circumference. So we're drawing a circle O as usual. So we're getting things in place. We're going to mark 2 points on the circumference below the center, and we're going to label them P and R. All right, so we're identifying the R there. And at another point, we're going to mark another point on the circumference above the center, and we are going to label this point Q. Great. Now we're going to put in the chords, and then we're going to measure the sizes of angles PQR and POQ. So we're measuring PQR, and the measure of that angle is 45 degrees, and POR is 90 degrees. In our instructions, that is supposed to be POR and not POQ. Let's go back. All right, good. Now, what did you observe? Share your observations in the chat. Ms. Hemmings, I don't know why they don't want to talk to us. You know, they prefer to type to us.
Yes, I'm following the chat. There isn't any new responses yet, and
Okay.
our Facebook, sorry, our YouTube, I keep saying Facebook. It's also going, but no new responses just yet.
All right. What did you observe? Something's supposed to jump out at you right here. So,
Okay, Shanika is coming up and also Shante with responses. Shanika is saying that angle at the center is twice the angle at the circumference when coming from the same arc. And Ashanti is basically the circumference is twice. Give that a second look, Shante. Um, Sabrina is saying that the points are on the circumference, but what is happening with those points at the circumference and the one at the center? It's not allowing me to unmute. Okay, just raise your hand, Il, and we'll unmute you if you'd like to respond. And Rikia is saying that the angle at the center is twice that at the circumference.
all right, good job.
And so is Giovanni, I think. Yes, he's identifying those angles by name.
All right, so we're looking at these properties. So we can see that the angle at the center is 2 times the angle that goes to the circumference of the circle standing on the same arc or chord. Or we could also say that the reverse relationship is true, that the angle at the circumference is a half of the angle at the center standing on the same arc or chord. Good. So again, remember, you're going to have to be able to identify this, not paying attention to the orientation, regardless of how it is structured, how it looks. We must be able to identify this same property. So does the property still hold when the position of the point A is changed from the major segment to the minor segment?
And this time, Mrs. Hayes, we're not going to give it away.
All right. So here, this is the question. Does the property still hold when the position of the point A is changed from the major segment to the minor segment? Again, look at where we are. We are in the major segment, and the major segment is that larger segment. All right. And the minor segment is the smaller segment. So look at the point A now. Imagine that the point A is no longer in the major segment, but it has been reassigned, or we change it, or we put it down into the minor segment. Will the property still hold? Somebody says they like
All right, Shanika is saying, I think it still holds.
they like to give us their caution
Yes,
statement.
yes,
I
I
think
think it will. And I'm here getting a lot of yes, misses.
yes, okay.
Not
All
seeing
right.
any responses on YouTube just yet.
All right. So let me know then, if we were to put the point A into the minor segment, what would be the measure of angle A? Let us say
Okay.
angle, it's now changed and we have placed it on the same, it's in the same, standing on the same arc or chord, and it is now in the minor segment.
Okay,
What
so
is the measure of angle A? 44.
they're still holding that yes, miss, it will still remain, and it's
I,
going to be 44.
I hear 44.
Are we giving it away now, Mrs. Sales?
All right, let's test. You can go ahead.
Go ahead.
Yes.
All right, we are there. Did it all?
Did it hold? That is the question. Did it hold? Or did we make a mistake with that value? It didn't hold? We need to talk to somebody, Miss Hemmings. We need
Sabrina and
somebody to
Shanika is telling
open.
us no, it didn't hold, miss. I'm
We need
Shane
to
is still insisting that maybe.
All right. Now, tell me where this angle is now, where angle A is. We made a mistake. Oh, let's see. Where angle A is now. All right. What is the size of the angle at the center? Based on where angle A is now, what is the measure of the angle at the center? Is it still going to be 88? Hmm?
Shane is saying 88 is it's twice 88.
It's going to be twice 88?
He's saying that the value that A is now is twice that at the center.
Okay. All right.
And on
Which
Facebook, they said,
which
yes, I think it will. So Facebook is saying, yes, I think it will still hold.
All right. Let us see. What is the size of the angle at the center now that is subtending the angle of 136 degrees at the circumference? What is the size of the angle at the center that is subtending the angle of 136 degrees? Let's look at it from that angle. So is 88 subtending that angle? Because 136, is it in the same segment as the 88? Hmm? No, it's not in the same segment. So what is the measure of the angle that will be subtending the 136 from the same arc or chord? It's easier for you to see in terms of the arc. What is the measure of the angle that is subtending, that holding up that 136, that arc? Do we need to, can we help them anymore, Miss Hemmings?
I think we should.
Okay. All right. So that angle, we're going to look at somebody say,
All
we
right,
did
Davia is saying, all right.
it.
Congrats to Davia.
All right. Right. And Shaniqua as well.
Yes.
So what we find is that it's the reflex angle on the outside of that 88 that is subtending the 136. And that angle is going to have a measure of 272 degrees.
So we can give it away now, right?
Yes.
It's
So that
okay.
angle, right. So that angle is going to have a measure of 272 degrees. And therefore, a half of that measure is going to give us that
All right.
136 degrees.
Could we get that response, please, on the slide?
Sure.
All right. Here it goes.
So there we go. All right. So we have that 272 and it is subtending that angle of 136 at the circumference of the circle. So if two angles stand on the same chord, when the angle at
Oops.
the center
We go
is
back. All right.
twice, sure, let's go back. The angle at the center is twice the angle at the circumference. So you recognize that we can see this property in two orientations at least here. We can talk about it in terms of the reflex angle, depending on where the angle is formed at the circumference of the circle. And we'll also look at it in terms of the acute angle as well, depending on where the angle is formed at the circumference of the circle. So you have to have your eye out looking for those properties. All right. And here are some other orientations that would give rise to the same concept. So in figure 1, we see that the chord AB, we have that angle at the center, and that angle at the center is going to be twice the size of the angle formed at the circumference. So if the angle at the circumference is x, then the angle at the center there is going to be 2 times x, which is 2x. All right, so that's for figure 1. Let's look at figure 2, which is similar to the second example we just looked at, where we're looking at that reflex angle there. So the chord there is AB, and if the angle here is x, then the angle, which is the reflex angle here, is going to be 2 times the size of angle x there. So you have to look out for that, all right? And in the case of figure 3, we know it looks a little bit different here. And sometimes you get confused, you know, you might confuse this one with the first one. But what's the difference between this figure at number 3 compared to the first property that we looked at when we said angles at the circumference of the circle standing on the same arc or chord are equal? What is the difference here with this diagram why we cannot use that property? Remember the first one, we said angles at the circumference of the circle standing on the same arc or chord are equal. Why is it we cannot use that property with this question? Come.
Yes. Waiting
Yes.
for the chat on for YouTube.
Yes. Why is it that we can't
Or
use
the
that
mic.
property for this one?
Let me
Yes,
see
we'd
if I
love to
see any hands
really.
up.
It doesn't have a chord. Of course it has a chord. It's standing on the same
Chord.
chord.
The
Right.
one
So you
point of the
don't,
chord is A.
right. You don't see the chord drawn here, but it's on the same arc. So why is it we can't use that property here? It's very important for us to distinguish, particularly in this orientation, because students make a lot of mistake because the chord is not where it was in the diagram 1. That's not the main thing. No,
Yes.
the orientation has changed. That's true. But
Mhm.
why is it that this property, why is it we could not use that property with this one? Let me remind you of that property. Angles at the circumference of the circle standing on the same arc or chord are equal. Does that property hold here?
I think I want to give him an hint, Mrs. A. Oh,
Yes.
we have the answer.
Somebody said yes.
Yes, Giovanni. Giovanni.
No,
At the
no.
stop at the center. He said it stop at the center.
It's, oh, I didn't see that one. Sorry.
Yes,
Yes,
but
it's
he
stop
needs to reword it. Where should it be? If it
right.
want it.
If
Yes.
right, if we were going
Yeah.
to use that property, the both angles would have to be at the circumference. Go.
Right. Davy, I
In
gave it
this,
away.
right, in this case, one angle is at the circumference, but the other is at the center. So we could not use that property. So we have to use this one, which we say that the angle at the center is twice the angle at the circumference standing on the same arc or chord. So if angle B should measure a value of x, then the angle at the center is going to be twice that value, which will therefore be 2 times x. All right, so we're back at this question now. We're back at our CXC type question, and we're looking to see the property angle at the center of the circle is twice the angle at the circumference standing on the same arc or chord. All right, let's go. Which two angles would we be able to say is displaying this property, and therefore this angle is going to be twice the measure of that angle, or that angle is going to be a half of the measure of this angle? Go. Let's hear
Right.
some.
No responses yet in the chat or
They're,
on
they're,
YouTube.
they're thinking. They're thinking.
Yes, we're giving them a little time to think about
C,
it.
C and O. Somebody
Oh,
said C and O. All right. What I want you to do, use 3 letters to describe the angles for me. Give me the starting point, where the angle is formed, and the
right.
ending point. All right. Give
All
me
right.
3 letters. So AOG. Yes. So what about AOG, Miss Lynn? Tell me what about AOG? AOG has a relationship with which angle? So we're seeing Hallie here saying ACG and
Right.
AOG. All
And
right.
Ricky,
So,
quite a few of them.
right. So what is the relationship now? So you told me that those 2 angles have a relationship, which I agree. So what is the relationship? Which angle is twice which, or which angle is a half of the other? Share that with me now.
I'm seeing on Facebook where Indy and fewer others are also saying O and C, but we're asking them to use the 3-letter naming of the angles
All
and
right.
then and starting point.
All right, so Shaniqua is saying AOG is twice ACG. Very good. And in the same vein, we could say that ACG is a half the measure of angle AOG. Good job. Good job. All right, so I see you zooming in, Here's another question. Do we have any other such angles in this diagram that display that property? Is there any other such angle in this diagram that displays that property, where the angle at the center is twice the angle at the circumference standing on the same arc or chord? Angle at the center, twice the angle at the circumference, standing on the same arc or chord. Do we have any other pairs of angles in this diagram that is displaying that property? Go right ahead. CDA, CDA. Let me go again. CDA, and I didn't see that one, Miss. Read the second one for me, because I was busy finding CDA. So I found
Okay.
CDA, but I am not seeing where there's an angle at the center coming from that. Remember, you can't draw a line in your mind, You have to use the angle. Sorry. You
I'm
have to
seeing a
use the
raised hand.
angle. All right, you have to use the angle, the lines that are already in the diagram. Sorry about that. Somebody's saying
No
they're not hearing me
problem.
clearly. All right. So I'm just trying to elevate the microphone to make that a little easier. So, I am seeing CDA, but I'm not seeing an angle at the center that is equal to,
So that.
that would be twice that angle at the circumference. So I would have to say no. All right. Is there any other peer? There was a raised hand. Would we like to open mic for that student just to share? Is there any other pairs of angles in this diagram that is displaying the property angle at the circumference, angle at the center of the circle is twice the angle at the circumference, standing on the same arc or chord?
I
All
think
right.
I think someone has a hand up to speak.
All right. Go ahead.
This is Barbara.
All right, Barbara. Good evening. Good afternoon.
Let's see if I can help her to unmute. Barbara, are you able to unmute yourself?
Is it BCG
BCG and
ACD?
ACD. All right. Identify the arc or chord first, and then go to the center, and then go back to the arc or chord, and then extend to the circumference and see if you can follow that. So if you said BCD, would be, if it were drawn, you would
No,
have a
I said BCG.
okay, BCG. All right, so BCG is the angle at the circumference of the circle standing on the chord BC. So I see that. All right, now can you give me the labeling for the angle that is at the circumference that is standing on that same chord BC? Which angle is at the center that is standing on the same chord BC? The only one that could possibly work for that would have been BOC, but there's no line drawn for OC. Are you following me, Barbara?
Yes, miss.
All right, there's no line drawn for OC, so we could not use that one.
I think we need to give them a little bit more clue for this one, Mrs. Neal. So
All right.
probably we could export,
So
we should
let's
share with them.
let them see the diagram that we're looking at. All
All right,
right.
so this would have
So
been,
this is our diagram. So we're looking at ACG. So ACG would be the angle. All right. Perhaps you'd want to mute, Barbara. Thank you. All right. So we're looking at, let's bring it back. So we're looking at ACG, which is the angle at the circumference. Let's go back. It's the angle at the circumference, ACG. We just go back one slide.
so
So,
this is the one that we're looking at now. One that they were unable to find.
okay. All right. So ABG would be the other. All right. So ABG, B is at the circumference standing on the arc or chord AG. And the one at the center is AOG. That one we have marked out in red. Are you seeing that? So AB, let's look at the chord or the arc, it's AG. And going up from AG, following up to the circumference, we'll find angle B. Then we come back down to AG. And going back up to the center, from the same chord, we find O. So that is the other pair. Right, no, we didn't draw any lines. But the line, there's an intersection. The line OG is actually lying on the line GB. So it looks like a straight line, but it's the same line that we're using for OG and GB. All right. So she said we should draw any lines, but we didn't. It's the same line, but part of it is OG and the other part goes, OG is a part of the line GB. All right. Okay. So that is one pair. So we see angle AOG is twice the size of angle ABG. And the other is ACG is going to be half the size of angle AOG. So AOG is twice ACG, and the other AOG is twice the size of angle ABG. All right.
And just to reiterate that the R that they should look out for here, sorry, the chord that is AG.
Is AG.
That's
But
the
because,
critical chord.
right, but because the chord is not drawn, we're working with the
The
arc.
arc.
Right. So we're looking at the arc AG. And that is why the properties say angles at the center of the circle standing on the same arc or chord. So if you don't see the chord, look out for the arc.
Arc.
All right. The arc is always there because it's a part of the circumference of the circle. So if you don't see the chord drawn, look for the arc. So angles at the center of the circle standing on the same arc or chord. Sorry, the angle at the center of the circle is twice the angle at the circumference standing on the same arc or chord. All right, good. So we're getting somewhere. All right, and just looking at another one, and we I think we are just at number 3, so we have to go a little
Right.
faster. All right, remember we have 8 to go. All right, so we're looking at angles in a semicircle. I'm just waiting for this to come up.
Visible, right?
All right, so again, we're drawing our circle, and we're going to draw, we're going to follow these instructions to identify where we're going to put our line segments within our circle, and then we look out for those properties. And seem to be a lull in terms of responding.
It's coming up. We could move the animation a bit faster.
All right, great. So we have the circle we would have put in the center, and we have identified the diameter. It says draw the diameter through the center. We know that the diameter is a special chord that passes through the center of the circle, touching 2 points on the circumference of the circle. And we're going to label the diameter. We're going to label the diameter BC. All right. Somebody telling us from now, so can't wait until we get there. So no problem. All right. So we're putting in the diameter, and then we're going to complete a triangle by drawing 2 chords in one of the segments, and they are going to be used to form a triangle, and that's going to give us the other vertex of the triangle in that segment. All right, so what we're going to do now, we want to identify, if we have this diagram drawn in a semicircle, what are the properties that would form in terms of the angles that are related here. So we're going to measure the size of angle BOC. So we go ahead and we're going to use our protractor, going to measure that angle, and we're measuring that angle, and it is a measurement of 180 degrees. And then we're going to go ahead and measure the sizes of the three angles formed at the vertices of the triangle. All right, so this base angle A here seems to measure 90 degrees. All right, and then we're going to look at the size of angle C here. We come around, we read it, and it's 45 degrees. We're going to look at angle B here. We come around and we measure, and it is also a measure of 45 degrees. Good job, protractor. All right, so here it is. What did you observe? And we want to hear the observations as quickly as possible because we want to make sure that we go through everything with you this afternoon. So angle standing on the diameter and is on the circumference is equal to 90 degrees. All right. All right, so good. So the angle, it's standing on the diameter, it touches the circumference of the circle, and that angle there that is formed at the circumference of the circle measures 90 degrees. All right, so BOC is a straight angle, good. All right, so this is another orientation of the same diagram. Can you tell me which angle here measures 90 degrees? Can you tell me which angle in this diagram measures 90 degrees? C. All right,
L.
what else gave it away? Apart from the fact that it's at the circumference standing on the diameter, is there anything else you see on that? The little box, good. That little box there is usually used to indicate a measure of 90 degrees. Now, when the angle stands on the diameter, and we found the size of angle C there, and that symbol, great. So the diameter is a straight line. So the angle at the center measures 180 degrees, and therefore, it is also going to be a part of the previous property that we looked at, where we say that angle at the center of the circle, and in this case, the center angle is 180 degrees, is twice the angle at the circumference standing on the same arc or chord. And the arc or chord that we're talking about here is going to be chord labeled. What's the chord that angle C is standing on at the circumference? Give me the labeling for the chord AB. Very good.
AB.
So AB is the chord, and of course that angle there measures 180 degrees, and it's subtending the angle C at the circumference of the circle, and therefore we expect for it to measure 90 degrees because it is a half of the measure of the angle at the center of the circle. All right, so the angle in a semicircle is a right angle. That's a nice, easy rule to remember, and we don't normally call it a rule. It's just something for you to remember as your reason whenever you do your calculations. All right. So this one was a nice little one. All right, we're back to this question now. How we can't leave it out, you know. We want to make sure that when you see this diagram, you can identify all the properties. All right, so let's look at this. Can we identify the property where angle in a semicircle is a right angle? Somebody says ACD, ACD. All right, before we get to that, there's a very important property that we must identify first, because it's not just that it's 90 at the circumference, but it must be standing somewhere. Where should it be standing? Tell me, where should it be standing? All right, somebody says BCG. All right, I see you. Where should it be standing? Just on any chord? It's 90 degrees at the circumference if it is standing on just about any chord. Where should it be standing for us to be able to say standing on the diameter? Very good. It must be standing on the diameter. Can you give me the lettering for the diameter in this diagram? A chord that is the diameter in this diagram. BOG. All right. So that is the diameter. So you have to identify the diameter. Thank you. Now, which angle is at the circumference and is standing on that diameter? Give me 3 letters for that angle. BCG. Very good. BCG is at the circumference and it is standing on the diameter. Very good. So the angle there, BCG, is going to have a measure of 90 degrees. Let's go back just to show them that one. So BCG there. So the diameter is BG, passing through the center O, and the angle at the circumference that is standing on that diameter is angle BCG, and that angle measures 90 degrees. So we say angle for our reason, we say angle in a semicircle is a right angle, or angle at the circumference standing on the diameter measures 90 degrees. All right, so we're going to go to the cyclic quadrilateral activity. And this will wrap up our first segment of related angles in terms of angles in circles. Again, we're going back to the process. We're going to draw what this looks like. We're going to put down our circle, and then we're going to draw our line segments to complete that quadrilateral within the circle. And we're just waiting for this to come up. All right, so we're going to draw our circle with center O, and then we're going to mark 4 points on the circumference of the circle. And where we have placed our points, it doesn't mean that you have to put yours there, because the property will still hold. That's a nice thing about math. All right, so we're going to put our 4 points so located. So we're going to put P, Q, R, and S at these 4 points. And then we are going to draw our line segments to connect those points on the circumference of the circle. And in doing that, we're going to see that we would have formed a quadrilateral, all right, within the circle. So it's important to note that with the quadrilateral, it's within the circle, and all the vertices of the quadrilateral are touching the circumference of the circle. And that's important, all right? And then we're going to check out some of the angle properties of these quadrilaterals within circles that we refer to as cyclic quadrilaterals. All right, so we're going to label the opposite angles, and we're going to measure them and see what property holds in this case. So the first angle that we're going to look at Q, and we're going to look at the angle also that is diagonally opposite to angle Q. So we measure angle Q, and the protractor tells us from there that it is a reading of 89 degrees. And then we're going to look at the angle S, which is diagonally opposite. So if we were to put in the diagonal, we would be up at angle S right there. So angle S here measures, let's see, it's not quite 90, it's a little bit off, so it's 91 degrees. Very good. Now, we want something to stand out clearly for you. So we're not going to measure the other two, but we're just going to identify the other angles which are also diagonally opposite here. All right, question. What did you observe? What did you observe? Opposite
All right.
All right.
Seeing some
Opposite
responses in the chat. They're
All right.
firing, Mrs.
Yes,
Hales.
they are. That's
And on
great.
YouTube, Chadwick is also saying they add up to 180,
All right,
180 degrees.
we're getting all the math terminologies that we want. We want to hear that they add to 180, and we also want to hear that they are supplementary. And that tells us that they add to 180. So opposite angles in a cyclic quadrilateral are supplementary. Very good. Exciting things. All right, so is it like, oh, you breeze through that now? You should be able to identify that as we continue to move on. So we're not staying long here because you would have seen that off the ball. So that's excellent job. All right. So we're just moving on now to see what our observations should have been. And again, you said it quite clearly, and this is our little reason that we will want to concretize. Opposite angles in a cyclic quadrilateral are supplementary. And again, we recognize that these angles don't always have to look the same way. They can be in different orientations. That means they can be positioned differently within the circle, but we must be able to identify them however they are oriented. All right, so let's look at this. All right, so we have the vertices of this quadrilateral A, B, C, and D, and we recognize that it is in the circle, and the key part that we want to pay attention to ensure that this is actually a cyclic quadrilateral is that all the vertices of the quadrilateral are touching the circle, the circumference of the circle. If it is you have a quadrilateral within the circle and the vertices are not touching this circumference, you do not have a cyclic quadrilateral. That's a very important point to make right here. All right. So again, we're going back to our big diagram. Everybody ready? Before we do that, just identifying again for you the angles that are diagonally opposite and that their measure The sum of their measure is 180 degrees. And we say that opposite angles in a cyclic quadrilateral are supplementary. And that again, just reinforcing, means that the sum of the angles is 180 degrees. All right, so let's see if it's time for us to look at this. No, we're not there yet. So now we're going to look at the exterior angle of a cyclic quadrilateral. And here we're bringing in other properties that we would have looked at before. So we see that angle Z is exterior to angle X, and angle W is exterior to angle Y. All right. Is there any property that you can identify that would help you to be able to calculate the measure of an exterior angle? Let's see what you're thinking. Put on your thinking caps right now. All right. So thank
Yes,
you,
Miss.
Shaw. Great. So tell me what you're thinking now. Type it out for me. Reasoning. We need to know your reason behind this. So yes, there is information that you would have had already that you should be able to utilize to figure out how you would calculate the size of the exterior angle. What are you thinking and how would you be able to accomplish that? Let us say that you knew the size of angle X. How could you find the measure of angle Z? You know the size of angle X, how would you find the measure of angle Z? 180
Okay,
minus
using the
X.
straight line.
All right. So, and then of course, you know, you need to give us a little reason. So we're going to say, all right, adjacent angles on a straight line sum to 180 degrees. Good job. All right. Let us say that you knew the size of angle X. How would you find the size of angle Y using angle X? How would you find the size of angle Y using angle X? So wait, so angle Y is also going to be 180 minus X? Something fishy. What is happening here? What does that mean? What is that telling you? Something happened there. What is that telling you? So angle Z can be found using the calculation of 180 minus X, and angle Y can be used finding the same 180 minus X. What are you thinking? What are you thinking?
I'm seeing Shanique saying Z and Y, they're equal.
Z and Y are equal. And in the same breath, which angle will be equal to angle W?
Opposite exterior equal interior opposite.
All right.
That's Rikia.
All right. X will be equal to
Equal to
W.
W.
All right. Good job. All right. So that is what we wanted you to identify. So going back a little, we see that angles, going back a little, we'll see that angle X is equal to angle W and angle Z is equal to angle Y. All right. Good job. All right, we're back here at our CSEC question to wrap up this segment, and we're looking to identify where the exterior angle is equal to the interior opposite angle. Can we identify that? We see any of that?
Or where the cyclic quadrilateral
Right,
theorem will come in.
right. But we can use either of those, but because we're focused on the cyclic quadrilateral, so let's stick with that. But can you identify a cyclic, the labelings for the vertices of the cyclic quadrilateral in this diagram? Labelings for the cyclic
David
quadrilateral.
saying A, B, C, D.
A, B, C, D. All right. A, B, C, D. Good.
And so is Cedric on YouTube.
All right. Is there any other? We have a lot going on in this diagram. Can you identify any other quadrilateral within this diagram that you can say is a cyclic quadrilateral? Any other? Are you sticking with A, B, C, D? Just A, B, C, D. You have B, D, C, G. Let me see. B, D, C, G, or you're saying, all right, well, look at that one carefully for me. I'm going to relabel it as B, C, D, G. But there's no line joining D. There's no chord going from D. We didn't draw a line for this diagram going from D to G. So that would not be a cyclic quadrilateral. All right. All right. So that's it. So let's just identify what our cyclic quadrilateral would look like here. And of course, you're correct, A, B, C, and D. And we recognize that the angles that are diagonally opposite, B and D, there is no more, right? The angles that are diagonally opposite, B and D, are supplementary. That means they add to 180 degrees. And angles A and C are also diagonally opposite, and they too are supplementary, adding to 180 degrees. All right. Trusting that you would have grasped these concepts and are ready now to stretch and move into the other segment. All right.
Thank you,
And
Mrs.
to
Ames.
take us through, we'll have Miss Hemmings. You're most welcome.
Okay, students, your participation has been great. The chat has been lighting up on YouTube as well. Thank you very much for participating. All right, so we are just going to be moving forward, and we are going to now be looking at angles between a tangent and a radius. All right, so angles between a tangent and a radius, we're going to be doing the construction as you would have observed from early example. So we're going to construct a circle. We're going to label it center O. Then we're going to mark a point outside that circle A. We're going to construct a tangent, and a tangent should only touch the circumference or cut the circumference at one point, not two, not three, just a single point. Then we are going to construct or mark the radius, draw a line for the radius OB. And then we are going to measure. So let me just go back a bit. We're going to measure the angle OBA. And I'm going to ask you, what is it that you have observed? What is it that you have observed after all that construction? All right. Where is the right angle forming, Shanique? Which two lines? Which two lines are responsible for that right angle triangle being formed? Yes. So it's very important that you highlight that the right angle triangle is formed between the tangent line or the tangent and the radius. So it's very important. So the observation that you should have made is that the radius OB is perpendicular to the tangent, which means that when those 2 points intersect, it's going to form a right angle. Very good. All right. So when the line OA was constructed, a right angle triangle was formed. So the primary thing that you need to remember with this particular theorem is that a tangent and a radii, when intersect like this, the tangent will bisect, not bisect, is perpendicular to the tangent, therefore forming a 90-degree angle. All right, as usual, we have a CXC spotlight question for you. Are you able to identify, thank you very much, Yvonne, are you able to identify that particular theorem that we would have discussed, where a tangent and a radii forms a right angle?
All right. Let's see what's happening in the chat. Somebody says, Kenistia. Oh, I missed
BGE.
that. Davia Blake says OGE.
Okay.
All right, let's go back here.
OGE. All right. Okay. OGE. All right. Any other responses?
We also have BGE.
BGE. All right.
We also have OGF.
OGF. Very good.
All right. And OGE.
Okay then. All right, let's see if our picture in picture agrees with the responses so far.
All right.
Oops. Let's take it back a bit. All right, so persons who gave those responses, very good. All right. So indeed, our responses, the expected responses, we can either start from O, but since we are focusing on the radius, we should actually be saying OBG, sorry, OGE and OGF. All right, so those answers are very good. Thank you very much. All right, let's move on now to another theorem. And this one focuses on tangent that forms from an external point to the circle. And let's see what happens in cases like those. So again, we are going to construct a circle, label it center O. We are going to mark that point external to the circle, construct our first tangent, then of course we insert the radius to show that perpendicular relationship, then another tangent called CAC is formed or drawn. Then we measure those two lengths. I want you to give keen observation to the lengths I'm measuring right now. First, I'm measuring AB, and then I'm going to move over and measure AC. If you're able to read those rulers, what would you have observed? And we kind of gave it away with those symbols too. And then we are going to measure these two angles, OBA, and we're going to,
because it says they are the same length.
all right, and we are measuring OCA as well.
Selena says they're equal.
Okay, let us see if we agree with Selena. All right, so we get an observation, but before I reveal what we have here, let's hear what the chat is saying. Okay, they're saying they're same length.
They have the same
Very
length.
good, very good. All right, let's see if our observations agree with you. All right, so they are of the same length, but some other things are also coming out. Realize that the radii, they are actually perpendicular to the tangents form. And we also realize that if we put in the chord BC, we get two isosceles triangles. Anybody realize that? That the point OC and OB, they're actually radii, and when they are connected with the chord BC, it forms a isosceles triangle. Anybody remember the relationship between the angles in an isosceles triangle? Anybody remember that relationship? When two lengths are equal.
We're referring to the base angle.
Yes, what happened to these base angles here? What can we say about them? Okay, are you responding to that question, Ale? Saying that they are equal in the isosceles triangle, the basal angles? Yes, they are indeed equal. I want you to take a look at this other triangle, the triangle CAB. Would you also say that triangle is an isosceles triangle? And if so, which two angles would be equal?
And you can go ahead and use 3 letters to identify those angles.
Right.
All right, CA and BA would be equal in length. I think this is what Hal is saying.
Right.
And then we want to see which base angles from that triangle ABC would be equal. And we're
right,
seeing
let us just
CAB.
go back.
All right, we're seeing Ricase is saying CAB and CBA.
All right.
CAB and CBA.
CAB
and CBA.
CBA. Okay then. All right, I think she probably.
Right.
All right.
She needs to have another look at those.
Right. Have another look at that.
Just based on the 3 letters that you're using. I think you know what you're saying, but I think you perhaps made an error with those.
Rearrange them
down. Right.
Right.
All right.
I'm seeing ACT. I think that should be a B.
Be a B, yes.
And ABC. All right. Okay, that's what we get the general understanding. So basically, you're seeing that these two angles at this point here in my isosceles triangle and the other angle here are all equal. But I want you to recognize something else. When I put in this line OA, which is the bisector of angle A, CAB, it also gives me another grouping of triangles. Can anybody tell me what is it that they observe about these 4 triangles that are formed? That would be triangle OCX or COX, whichever order you want to call the letters in. CAX,
Regina,
BAX. Okay, how many right angles are we getting there, Regina? How many right angles are formed? 4, excellent. So you realize that a lot of rich concepts are coming out when we have 2 tangents being formed at a common point outside of the circle. So we have 2 isosceles triangles being formed, 4 right angle triangle being formed, and you can use those concepts to determine the measures of angles and length. But the most important, you want to recognize that when 2 tangents form at a common point outside the circumference, the length of those 2 tangents are, the lengths are going to be what? Equal. Very good.
says equal.
All right, very good. All right, so we'll now proceed to another one. All right, Ailey is saying supplementary angles could be applied. Yes, because the sum of angles within a triangle would give you 180. Okay, I'm showing that too fast. All right, so we just explored where we have 2 tangents forming at a common point outside of the circle. Are you able to identify where that would apply in this question? And if that is the case, what would be the relationship between the, what should I say now, the lengths that you have identified? Or would that particular concept apply in this case? All right, so Shanique is saying that tangent AE is equal to tangent BE and they are equal in length. Okay, so both persons are equal in length. How about angle? What would you say about angle OAE and angles OBE? They are what? Both 90 degrees and they are both equal. Very good. All right. So we are still moving along. All right. Can you, because we're not going to assume that you have been following us and you have been picking up the things that as we go along. Are you able to identify any of the other theorems that you'd have covered so far in this question? Any other stood out to you immediately?
All right, look very carefully.
All right, I'm getting an answer from Shanique. She's saying I'm seeing a cyclic quad. Okay, can you identify the points on that quad?
Right.
Okay, Selena is saying quadrilateral something. All right, Selena, can you identify the points on that quadrilateral? Because I'm seeing a lot of 4-figure things in this. I don't know which one you're talking about.
CABD.
Okay. CA. Okay, all right. Okay, very good. Any other theorem comes out at you? Anyone? I think I'm seeing at least one other. Ah, very good, Shanika. You spotted that one. So you're seeing where the angle at the center is twice that. Once they are subtended by the same chord, twice that the one on the circumference. Very good. And the tangent and the radius forming a 90-degree perpendicular. Very good, very good. Very good observation. Let us see if our picture agrees with you. And indeed it does. So we would have seen this cyclic quadrilateral coming out as well as angles at the center be twice that at the circumference once they are subtended by the same arc or chord. Okay, very good. Good going. So we are going to be taking a look at another theorem that is referred to as the alternate segment theorem. All right. So let us see what that involves. So again, we construct our circle. We label it center O. we construct a point outside. So immediately you know that a tangent is coming up, right? So we draw a tangent line or tangent AB. We draw a chord BC. We are going to be measuring that angle that is formed between that chord BC and the tangent. All right, realize that the tangent is 40 degrees. Then we are going to construct two other chords that form the right angle, not necessarily a right angle triangle, let me correct that. Two chords that form a triangle using the first chord, AC. And the point of that, oh, this is moving automatically. Okay, let us just stop this for a bit because our observations are being given away. All right, so at this point, we are going to measure the angle. And I wanted to observe, we inserted or we drew two other chords, BD and CD. And those two chords, along with the first chord, form a triangle and they meet at a point B on the circumference. I want you to observe that the segment, the alternate segment that we are making reference to is the segment that is now in pink. And I want you to observe that when we measure the angle CDB, what is going to happen? All right. So you recognize that that angle, I'm sorry. Sorry about the transition. We're having some problems here. So let me just restart. Thank you for your patience. So let us get back to where we should be. All right. So we realize that when we measure angle D or angle CDC, CDB in the alternate segment, we observe something. And I want you to tell me what is it that you have observed. All right. So I want you to pause right there. Let's hope it doesn't move. All right. What is it that you have observed? Okay. I'm seeing Khadija in the, is that a new response? Yes, it is. Angle between the tangent and the chord are equal to the one in the alternate segment. All right. Okay, let us see if we are in agreement with that observation. Yes. Angles CBA is equal to angle C. Okay, I think you have the names of the angles CDB. Right, very good, very good. Miss, because they are on the same chord, they are equal. Angles on the same chord at the circumference are congruent. Yes. So the angle that is formed between the tangent and that chord and the angle that is formed at the circumference, they're congruent or they are equal. Very good observation. Would you be able to find another pair of angles that are congruent in this same case? Let us see. Please note that the angle also formed on the other side of the tangent, not with chord BC this time, but with chord DB, that this 80 and the angle in the alternate segment. Oh, I'm sorry, the slides are moving faster than I'm touching them. All right, so I'm back now. That angle BDBX is also equal or congruent to the angle in the alternate segment, which is BCD. So it's two pairs of congruent angles you are going to get when you see this formation. And this formation occurs when you have a tangent line, a tangent, and a chord. Or in this case, two or three chords that are intersecting or touching the tangent. All right? So just a summary of the same concept we'd have observed earlier. So the tangent is formed, these two chords, realize that the angles between the tangent and the chords, they are equal to an angle in the alternate segment. So these two pink angles are equal. which would be angle ACD and angle ABC, it's equal. And these other two pairs, which is BCE and BAC, they're
Thanks for coming.
also equal. Okay, all right. Thank you, Giovanni. All right, so having looked at that concept, alternate angles in segments or alternate segment theorem, are you able to identify that particular theorem in this question?
All right, so we're giving them a chance to
To
look at it
respond.
carefully.
All right, I'm looking at Facebook.
Right, and to
Sorry, YouTube.
YouTube. All right. Let's see what responses we will get.
All
We're
right.
looking at that property, angle.
Angles that are formed between a chord and a
Okay,
tangent
is equal
is
to the
equal to
angle in the
angle in the
alternate segment.
alternate segment.
All right, so we have Shaniqua is saying BGF is equal to BCG. So let's verify that
B,
BCF is
okay. Oh, you're muted, Mrs. Hales. All right, so it's BGC, okay.
all right. We're seeing FGB is equal to BGF, and that is coming from Ricacia.
All right.
FGB is equal to BGF. Let's verify that one.
CGE,
I think she corrected to say
BGF,
BGC.
BGC,
Okay.
BGC. All right, let us see if that is the case. All right, any other responses?
Not at the moment. So
All right,
let's
I'm
see
checking on.
BGF and BGC.
All right, so let's
Sorry,
look at those.
FGB. Sorry, FGB, FGB, and
FGB
BGC.
and
FGB and BGC.
BGC. All right. Please note that just one point I want to make. The alternate angle would have been formed at the point at the circumference. All right. So that is my response to Rikia, just to take another look. All right. So B, I'm seeing another response here. CGE and BCG. Okay.
All right, and from YouTube we have CDB is equal to the exterior angle ABC.
Could you repeat the first angle? CBG. I'm not hearing you. You're on mute.
Sorry about that. CDB
CDB.
and ABC.
Okay, then. All right. So I think I'm going to be sharing our responses with you. Were you able to identify any of those pairs? All right. So the angles that we have expected you to identify, because we just did one pair, but we are going to identify the second pair together, is CGE. Let me see if I'm seeing that one in anybody's response. And CBG.
Yes,
Yes,
Shaniqua had that.
Shanika had that.
Yes.
But there's another pair that we didn't put in this diagram. Could anyone identify that pair? And that pair of angle would have been formed between the tangent EF and the chord, which in this case is the diameter of BG. Can you identify that pair as well? So I'll give them a few more seconds to see if anybody is able to identify that other pair.
All right.
BGF. So I'm giving you one of the angles actually. So BGF is the one that is formed between the chord and the tangent. Would you be able to identify the pair that the other in the pair that is equal?
All right. I think
Okay. So I'm seeing
Shanika gave a response as
All
well.
right, I'm seeing BCG. Okay. Yes, is that name Tar? How do you pronounce that name? Tarira or Taria?
Taria.
Taria.
Sure.
Oh, I'm getting the correct pronunciation.
All right.
All
But
right, Taria, very good.
Miss Williams. All right. Right. So we got some correct response.
Yes, so that's the response that we're looking for. And this is actually that response. So you're now seeing the solution to the second pair that we would have expected you to find. All right, very good. And I think on YouTube, they're also providing a response. So we are going to be looking at another theorem, and this one is called a perpendicular bisector of a chord. So again, we're going to start with the construction of our circle. We're going to label it center O. We're going to draw a chord called AB. And then we're going to find the midpoint of that chord. Then we are going to construct the radius OD to intersect the chord at its midpoint. What do you think is going to happen when that occurs? What is it that you observe? We're going to measure those two angles, but even before I show the measurement, what do you think the size of those angles are going to be? Okay, Sharika is saying 90. Do we have any YouTube responses? What do you think the size of angle OCA and angle OCB is going to be? Okay, Thomas is joining in to say 90 as well. What do you think is going to be the length of, oops, coming up way faster than I expected. What do you think is going to be the length of AC and BC? What could you say about those two lengths? Okay, I'm seeing 45 from Thomas as well. What could you say about the length O, AC, and BC? All right, Ale is saying they are equal. All right, let's see if we agree with you, Ale. All right. So yes, based on Thomas and Richard and Shanika answered, the angles form where the radius bisects the chord AC. They are actually 90-degree angles, so they are right angles. And the lengths AC and BC are going to be equal. And there's a reason why they are equal. And I'm going to use my annotate tool to show you why those two lines are going to be equal and why the angle formed when it's bisected by that radius is 90 degrees. So let me just grab my pencil here. I want you to observe that if these two lines were connected, OA and OB, oops, let us try and see if we could get back to that first. Thank you. If those two lines were connected to those points, what could you say about these two lines, OA and OB? And yes, it forms the isosceles triangle. And OA and OB would be what part of the circle?
Or what was the name that we would give to OA?
Yes, OA and OB. Yes, radius for one, radii for two. Very good. So the fact that we have an isosceles triangle, and we bisect it at this point, we are going to be getting right angle triangle here because it's a bisector, meaning that we cut it in two. When you have an isosceles triangle and you divide it in this form, you're going to get two right angle triangles. That is why we end up with a right angle when we have the chord, which forms the basal length of that isosceles triangle, when it's bisected, it's going to be cut into two equal parts. So it's actually a perpendicular bisector. So it doesn't just cut it in two, it cuts it into two right angles, two equal lengths, and two right angles are formed at that point. So it's important for you to remember, even if these two lengths are not drawn, remember if you have this case where you can form an isosceles triangle and you have a radius bisecting the chord, then it's going to form two right angles and these two lengths are going to be equal. All right, so let's clear my screen and then see if we can attempt a question or look at a question that brings out this theorem. All right, so as usual, our spotlight CXC question. Would you be able to, I didn't click on that, comes up on my screen. Would you be able to identify that particular theorem in this question? Where would it occur?
Or which angle would measure 90 degrees based on that theorem?
Theorem, right, thank you.
I know they're thinking, so we're giving students
Them a
some
few
time
minutes.
to
All
think,
right.
right? I'm not seeing anything in the chat just yet.
All right, I'm still giving them a few seconds.
All right.
All right.
We have ACE, is it?
AGE,
AGE.
right? Let us see if we agree with
Well,
that.
OGE. I think it's OGE.
OGE, all right.
And ABG. Somebody says ABG.
ABG,
Mhm.
all right. A, B, and G. All right, let us see. So in the interest of time, I'm just going to share our response. So the chord that we are going to be bisecting is going to be AC. So AC is the chord and the radius that bisects AC is going to be OB. So the two right angles will be formed at O, this point, C, this point, and O. We call that point X in the diagram, so I can call it CXO and OXA. So those are the two right angles that we are looking for. And the length AX and CX, they are both going to be equal. All right. All right, let's try. So we have basically gone through all 8 theorems. Very good. So Mrs. Ale, it's time for our CXC question options. So this is our first set of questions. So far we have exposed you, or we have given an opportunity to review all 8 theorems. Now it's time for you to demonstrate to us that you can apply them. So we have some CXC questions we are going to be shared with you now in the last segment of our workshop, and we're going to be asking you, how would you be able to find the first angle that you are being asked to find in this question? You have to give reasons for your answers. Remember those theorems that we went over? How would you be able to use those theorems to find angle OUZ, UVY, and UWO?
All right, so we'll give you a little time. I'll read the question through for you while you go ahead and work. We would like to take responses from as many students as possible as usual. So let's go. The diagram below, not drawn to scale, shows a circle, center O. The line UVW is a tangent to the circle. ZOXW is a straight line and angle UOX measures 70 degrees. Calculate given reasons for your answers, and that's important. You're told that you need the reason, and it also carries a mark at least. So it's important for you to be able to give your reasons. The measure of angle OUZ, UVY, and UWO. Now, When you give your responses, you must give your answer. And also, when you see these questions, don't just look at the diagram and jump to answering the questions. Always read what is written above the diagram in relation to the question, because there might be information there that is not represented on the diagram that will be useful to assist you in answering the questions. All right. So we're looking at O, U, Z. Any responses? O, U, Z. How would
All
you
right.
calculate the size of that angle?
It is saying that OUZ is an isosceles triangle.
Angle. OUZ is an isosceles triangle. That is true, because O is at the center and OU would be a radius and OZ is also a radius. So that would form an isosceles triangle. Good. How then can you calculate the measure or the size of angle OUZ? What are you going to do? You have a measure of 70 degrees there to help you. What would you do with that 70 degrees? That would help you to find OUZ.
All right. K Akia is saying that Z and Y they are 35 degrees. But remember, Akia, one of the very important things is that you have to give a reason. Okay, she's saying that there are alternate angles. Alternate angles are equal. I'm not seeing that particular theorem coming out here.
I'm not seeing it.
Sorry, either. But there's another one that you can use in terms of the isosceles triangle that was mentioned earlier. Right. Correct. So I'm seeing Shanika coming up with that idea as well. So because you know that those two angles, because the lengths OZ and OU, they are actually radii, they are going to be equal in length. So the angles formed between the chord UZ and those two lengths, they are going to be equal. So you can use the straight line, knowing that sum of an angle, adjacent angles on a straight line, they sum to 180. So the fact that you already know one of the angles on the line Z or XZ, you can use that to determine what angle Z or U is going to be. And once you find that angle, you already know what sum of the angles in a triangle should be. So you can find the other angles that are equal. Okay, very good. And I see someone running ahead. Is that the response to the second question, Ian? All right, so I think they're ready to move on. So let us move on. Let us show them how they should have been able to find angle OUZ. So the fact that you identified that it's supplementary angles 180, isosceles triangle, those two basal angles are going to be equal. You divide the remaining angle. Once you have subtracted, you got 110 here. You know that 110 is going to leave with all the 70. Accounting for these two angles, divide that 70 by 2, and you'd have found those angles. All right, very good. All right, let's look at the second one. Can you identify what would be the measure of angle U, VY, and Y? I'm seeing the answer from Ale. Is that a response, Ale, to this question, or it was for the previous? Is there any responses from YouTube?
Checking on that.
All right. Okay. So can you think of any? Yes. So, but Rikia, which one of the theorems did you apply? Which property did you apply in order to solve that problem? Remember, and apart from just doing the computation, you're going to be required to give reasons. So it's important for you to give reasons. Yes, the answer you provided looks accurate, but what reason, how did you come about that response? All right. Right angles in a semicircle sum to, okay. Right angle semicircle and sum of angles in a right angle triangle. Okay then. So you would have identified that this triangle here is a right angle, but additionally this one is a right angle because the tangent and the radius, they are going to form that right angle triangle as well. Okay, okay. But how would you word that? All right. Okay, so you would have recognized that the tangent OU is the perpendicular to the, sorry, the radius OU is perpendicular to the tangent UVW. So you know that immediately you have a right angle triangle here. You know that the sum of the vertex angles in a right vertices angle in a right angle triangle is 180. So you would have used that knowledge. You know that these angles, they're subtended by the same arc UX. So if this angle Z is 35, this angle Y is also 35. So you could also use that knowledge. All right. So indeed, the angle is 55 degrees that we're looking for. But apart from just doing the computation, it's important for you to state and to explain which theorem was applied or which particular property was applied in giving your answer. All right, so let's take a look at the final question, final part for this question. All right, angle UWO. So we are looking at this angle right here. What can you tell me which one of the theorems could we apply in this case to determine the size of angle? Okay, Rikia again is giving us the response, the answer. But Rikia, how did you get that?
Some of the angles in a triangle, angles in a triangle. Those are the responses.
All right, but which triangle are you making reference to? Because I'm seeing several triangles here. Yes, all of them will have a sum of 180 degree, but which one of the triangles did you use?
OUW.
OUW. So this elongated one. And what can you tell me about that triangle? Because notice all of the angles weren't given explicitly, you know. I only see a 70 here. So how you end up with the 90? How you know it was a right angle triangle? Davia. Oh yes, it's a right angle triangle, but then you have to identify which of the theorems, how did you know it was a right angle triangle? Because you weren't given the size of angle OUW.
Says
With
tangent and radius.
right. So the radius is a perpendicular bisector of the tangent OW. Right. So you already know if that is the case, this is going to be 90. So you have 70. The sum of the angles with vertices angles within the triangle should be 180. Just work out the difference and that will give us our answer for here. Okay. Let us see. Right. There you go. All right, so that would have concluded our session for this afternoon. But before you go, we have a post test that we'd love for you to do. So let me just go down. There are some other questions here you could practice with. I think these will be made available to you. Okay, post test. Those of you who have the scanner, the QR scanner can scan the code. And I'm going to ask our technical person just to post the link for the test in our chat for those of you who might not have the scanner to use.
As well as the link for our evaluation.
Correct, thank you.
All right, so before you go, you're gonna take our post test as well as we're asking you to complete or the evaluation for this afternoon session. You'll see a link coming up in the chat shortly. And just give us some feedback as to what you thought about the session and how it was for you. All right, so we're having that link coming up shortly.
All right, so the second link in the chat would be our evaluation link. Thank you for your participation. Are there any questions before you go? Let us know if you're able to access the post test and the evaluation forms if you're having any difficulties.
It was absolutely a pleasure, Ms. Hemmings, to go through these concepts with these students today. And we're hoping that it would have enlightened those who have never been introduced to the topic, as well as those who are just getting a refresher. So it was indeed a pleasure. And thank you for staying with us, students. And just continue to practice. And we pray that you will do well on your exams.